Nozzles and diffusers. Nozzles, diffuser. A nozzle is a device that increases the velocity of a fluid at the expense of pressure. A diffuser is a device that increases the pressure of a fluid by slowing it down. Nozzles and diffusers are commonly utilized in jet engines, rockets, spacecraft, and even garden hose. The derivation of equation of nozzles and diffusers. Summation of M in equals to summation of M out. M1 equals to M2. E in equals to E out. Q net plus summation of M1 multiply H1 plus V1 square over 2 plus GZ equals to W net plus summation of M2 H2 plus V2 square plus GZ. M multiplies H1 plus V1 square over 2 equals to M multiply H2 square plus V2 square over 2. Examples of problem solving. Example 2. Steam at 0.4 megapascal, 300 degrees Celsius enters an adiabatic nozzle with a low velocity and leaves at 0.2 megapascal with a quality of 90%. Find the exit velocity in meter per second. Example 2. Solution for example 2. Define the system. Now we are going to draw the system. Point 1, point 2, P1, T1 equals to 300 degrees Celsius and P1 equals to 0.4 megapascal. And P2 at the outlet, at the exit, P2 equals to 0.2 megapascal. Now, given that P1 equals to 0.4 megapascal, P2 equals to, at the exit, P2 equals to 0.2 megapascal. T1 equals to 300 degrees Celsius. We apply this conservation of mass. Summation of M in equals to summation of M out. M in at the point 1, M1, and equals to M2 at point 2. E in equals to E out. E at the entrance and E at the exit. Q net plus summation of M1 multiply H1 plus V1 square over 2 plus GZ equals to W net plus summation of M2 multiplies H2 plus V2 square over 2 plus GZ. M1 plus M multiplies H1 plus V1 square over 2 equals to M multiplies H2 square plus V2 square over 2. Neglecting the inlet kinetic energy, the exit velocity is V2 or V out equals to square root of 2 multiplies H1 minus H2. From the table A6, we are going to find the properties of the material in the nozzle. From the superheated table, P1 equals to 0.4 megapascal and P2 equals to 0.2 megapascal. T1 equals to 300 degrees Celsius. Now we refer to the temperature of 300 degrees Celsius. So the P1 equals to 0.4 megapascal. Now the enthalpy of the steam is 3067.1 kilojoule per kilogram. From table A5, the saturated mixture table, P2 equals to 0.2 megapascal, X2 equals to 0.90, HF equals to 504.7 kilojoule per kilogram, HFG equals to 2201.6 kilojoule per kilogram. H2 equals to HF plus X2 HFG. H2 equals to 504.7 plus 0.90 multiplies 2201.6. H2 equals to 2486.1 kilojoule per kilogram. We apply the conservation of mass. Summation of M in equals to summation of M out. M in equals to M2, E in equals to E out. Q net plus summation of M1 multiplies H1 plus V1 square over 2 plus GZ equals to W net plus summation of M2 multiplies H2 plus V2 square over 2 plus GZ. M multiplies H1 plus V1 square over 2 equals to M multiplies H2 square plus V2 square over 2. Neglecting the innate kinetic energy, the exit velocity is V2 equals to square root of 2 multiplies H1 minus H2. V2 equals to 1078 meter per second. Turbines and compressors. Turbine, compressor. A turbine is a turbo machine with at least one moving part called a rotor. Rotor assembly is which is a shaft or drum with blades attached. Moving fluid acts on the blades so that they move and impart rotational energy to the rotor. A compressor is capable of compressing the gas to very high pressures. A fan increases the pressure of a gas slightly and is mainly used to mobilize a gas. Pumps work very much like compressors except that they handle liquids instead of gases. The derivation of equation of turbines and compressors. We apply the conservation of mass, which is summation of M in equals to summation of M out. M1 equals to M2, E in equals to E out. Q net plus summation of M1 H1 plus V2 square over 2 plus GZ equals to W net plus summation of M2 H2 plus V2 square over 2 plus GZ. Q in plus MH1 equals to Q out plus MH2. Examples of problem solving. Example 3. High pressure air at 1300 Kelvin flows into an aircraft gas turbine and undergoes a steady state, steady flow adiabatic process to the turbine exit at 660 Kelvin. Calculate the work done per unit mass of air flowing through the turbine when A. Temperature dependent data are used, B. Cp average at the average temperature is used. C. Cp at 300 Kelvin is used. Solution for example 3. Firstly, derive the equation. The mass conservation of equation, summation of M in equals to summation of M out. M1 equals to M2, E in equals to E out, Q net plus summation of M1 H1 plus V1 square over 2 plus GZ equals to W net plus summation of M2 H2 plus V2 over 2 plus GZ. 0 plus M1 H1 equals to W out plus M2 H2. W out equals to M multiplies H1 minus H2. W out equals to W out over mass equals to H1 minus H2. Using the air tables, table A17 at temperature at T1 equals to 1300 Kelvin, H1 equals to 1395.97 kilojoule per kilogram. At T2, which is 660 Kelvin, H2 equals to 670.47 kilojoule per kilogram. For 3A, we apply the conservation of mass, summation of M in equals to summation of M out. M2 equals to M1 equals to M2, E in equals to E out. Q net equals to summation of M1 multiplies H1 plus V1 square over 2 plus GZ equals to W net plus summation of M2 multiplies H2 plus V2 square over 2 plus GZ. 0 plus M1 H1 equals to W out plus M2 H2. W out equals to M multiplies H1 minus H2. W out equals to W out over mass equals to H1 minus H2. W out equals to 1395.97 minus 670.47. Then W out equals to 725 and 0.5 kilojoule per kilogram. Now, using table A to C, we look at the air, the substance which is the air. The T average equals to 980 Kelvin. So the Cp average equals to 1.138 kilogram Kelvin. 3b, apply the equation of summation of M in equals to summation of M out, M1 equals to M2, E in equals to E out. Q net plus summation of M1 multiply H1 plus V1 square over 2 plus GZ equals to W net plus summation of M2 multiply H2 plus V2 square over 2 plus GZ. So 0 plus M1 H1 equals to W out equals to M plus M2 H2. W out equals to M multiplies H1 minus H2. So W out equals to W out over M equals to H1 minus H2. W out equals to Cp average T1 minus T2. W out equals to 728.32 kilojoule per kilogram. Using table A2A at temperature equals to 300 degrees Celsius for the air, Cp of the air equals to 1.05 kilojoule per kilogram Kelvin. Now for the question 3C, we apply the equation like the previous slide. To find the W out, we apply W out equals to Cp multiplies T1 minus T2. W out equals to 643.2 kilojoule per kilogram. Now for the throttling valve. Okay, this is the throttling valve, which is an adjustable valve, a porous plug, a capillary tube. Throttling valve are any kind of flowing restricting devices that cause a significant pressure drop in the fluid. The pressure drop in the fluid is often accompanied by a large drop in temperature, and for that reason, throttling devices are commonly used in refrigeration and air conditioning applications. The temperature of an ideal gas does not change during a throttling, which is H equals to constant. The enthalpy is constant. Process H equals to HT. Now, the derivation of equation of throttling valve. From the diagram of a throttling valve, it has the throttling orifice and also the control surface. Now, at the entrance, we label as point 1 and the exit we label as point 2. Energy balance for the throttling valve is the H1 equals to H2. U1 plus P1 V1 equals to U2 plus P2 V2. Internal energy and flow energy is constant. During a throttling process, the enthalpy of a fluid remains constant, but internal and flow energies may be converted to each other. Examples of problem solving. Example 4. One way to determine the quality of a saturated steam is to throttle the steam to a low enough pressure that it exists as a superheated vapor. Saturated steam at 0.4 megapascal is throttled to 0.1 megapascal, 100 degrees Celsius. Determine the quality of the steam at 0.4 megapascal. Okay, for solution example 1, firstly, we define the system. We draw the system and we label the entrance and the exit. The entrance is point 1 and the exit is point 2. And it also has the small hole, which is the throttling orifice. Okay. The pressure at the entrance equals to 0.4 megapascal and the pressure at the exit equals to 0.1 megapascal, and the temperature given for exit T2, which is T2 equals to 100 degrees Celsius. Now, we apply the conservation of mass and also the conservation of energy. Then, we expand the equation, which is actually the combination of equation of conservation of mass and also combination of energy, conservation of energy. And then, we get M1H1 equals to M2H2, H1 equals to H2. M1 equals to M2 because it is a single pipe. So the mass that enter the system equals to the mass out of the system. So we can simply cancel out the M1 and M2. From table A6, which is the superheated table, okay, we refer to the temperature. Given that P2 equals to 0.1 megapascal, T2 equals to 100 degrees Celsius. So at the 100 degrees Celsius in the superheated table A6, we are going to find the enthalpy H2 equals to 2675.8 kilojoule per kilogram. Now, H1 equals to H2, H1 equals to HF plus X1 HFG at pressure 0.4 megapascal. X1 equals to H1 minus HF over HFG. X1 equals to 0. After we substitute the values, and we get X1 equals to 0.971.